Okay, all right. Well, happy week 10 Friday. Last lecture, I guess, of the entire year. And this, I guess, our last time meeting in person. So thank you for coming and being here. And those of you online, I missed you guys. All right. Let me talk a little bit about the final exam. So I posted this document just now on Canvas. And well, it's loading. Okay, I don't know what's going on. Here it is on my on my thing. Okay, exam is Wednesday, December 7th, 3 to 6 p.m. Some students have emailed me about conflicts, and I'm sorry I have not replied yet. I'm looking at Friday. 3 to 6 p.m. Friday, December 9th, 3 to 6 p.m. I'll send an email to everybody who so they couldn't make it at because a conflict or something. But we'll go from there. Okay, so you're gonna take it at home, or I mean, it doesn't have to be at home. You could go to the library or something, some place where you can work in a on your computer. So you need to have reliable internet, and you're going to log into Zoom during the exam. So it's even though it's at home, it will be synchronous. So you will log into Zoom. I'll send out a link, and it will be proctored via Zoom. Please no virtual backgrounds. Please don't blur your background, and it's mostly there just to kind of make sure you're like working on the thing by yourself, and you're not like having a final exam party and taking the exam with other students or something like that. It being at home and also just knowing how things work. It's open note, open book, and opens most of the internet. Okay, I've given links to like official Python documentation sites, which I think will be helpful. But you are allowed to look at kind of other sites, so you can, go on Google and, look for things on Stack Exchange or things like that. The one thing you're not allowed to do is you're not allowed to post new questions and hope somebody answers your question for you, okay? This is something you got to figure it out on yourself, okay? So don't post questions to sites like Stack Exchange or Chegg. Obviously no collaboration allowed. This is like, can you do this? And it's very important that you don't share the exam file, don't post or distribute the exam files, or don't put it on your GitHub, or don't be like, oh, here's my solutions or something. Okay. And the way the exam will look is it'll kind of look like a homework assignment. And like I posted Jupyter Notebook. I'll post probably some kind of data file as well. And you will open it up and you'll work through that data, okay? I guess I forgot what I covered on. So I think week 9 I did SQL and then this week 10 we're doing like scikit-learn or stats models or things like that. And so I'm not going to put that on the final. There's kind of two major parts, all right? One is going to be data manipulation, summarizing, visualization with pandas and matplotlib, and Seaborn is included in that. So I recommend reviewing lectures that cover those tools, NumPy, pandas, matplotlib, Seaborn, a lot of kind of pandas stuff. So look at something like in homework 4. Where you did a lot of pandas work is there, okay? So I'll provide some kind of CSV file. You'll read it in with pandas. And these are things I might ask you to do. I'm probably not all, and I mean, it's even possible I'd ask you something that's not specifically mentioned on this list, but this list kind of covers a lot of kind of different things that you might have to do. So, you might have to change the index, or you might have to create, a date-related index. You might have to re-index the data and fill in missing values, or subset the data based on some kind of criteria. You might have to do some grouping of the variables and calculate the mean or some other summary statistic like the standard deviation or something like that for each of the different variables and groups. You might have to create new columns. You might have to calculate correlations between variables or create a line plot, things like that. I might ask you to create some bar plots or line plots, bar plots. You might have to have legends and stuff. So kind of, I guess, be familiar with the plotting tools. A lot of the things you can kind of plot directly using, from pandas. You can do like pandas.plot, whatever your, pandas data frame .plot type of thing. And so that's that. I will probably also throw in a function that was not explicitly taught in class. I'll give you the name of the function you can use, and you'll have to find the appropriate help page, read about that function, and be able to use it, okay? Because that's going to be an important thing to do, right? Within 10 weeks, there's no way I can cover everything. And so you really have to be able to read documentation and try something out. And so, as you study, it's not a bad idea to just look at some of the documentation. I mean, there's going to be, a ton of stuff, but you can just be like, okay, can I figure out how to use some kind of function that exists? Also, kind of like the homework, don't load in like extra libraries or modules that I haven't covered in class. So basically, you should be able to do everything with kind of the, most of these modules, right? NumPy, Pandas, Matplotlib, things like that, okay? Does that kind of make sense? Any questions or something like that? And then also important is, just explain or elaborate any of these kind of findings. I might be like, okay, so what does this graph tell you, or something like that. Okay, and then the other part will be some Python programming, and so I will I'll ask you to kind of create some functions, and so most likely you'll have to create, and again, I'm fine-tuning this, but you'll have to create some kind of class definition, and within that class definition, you'll have to implement some of these kind of special functions, the double under functions, like, less than or add or length or get item, the string representation that gets called when you call print, and things like that. And then obviously if you implement a method, you have to be able to define some kind of function as well. And so, I guess make sure you can do a little bit of problem solving and a little bit of kind of function writing and coding there. Some of it will have to do with, manipulating strings and tuples and lists and dictionaries, things of that nature. So, append and, get items, or, do, slicing of a string or stuff like that. Is that okay? Questions? All right. So that's what we've got. Okay. And then you'll, render the notebook and put that onto Gradescope, and then upload your kind of raw Jupyter notebook to Canvas. So very similar to a homework assignment in terms of like I'm going to post something and you download those things, you edit it, and then you upload your kind of the ones with the answers back online. The biggest change or the biggest difference between a homework is that, for a homework, I usually give you about a week, maybe a little bit longer to get it done. And here you're going to have 3 hours. Okay. And so, part of learning a language and becoming proficient and fluent in it is like, you can do stuff at a reasonable speed without having to like look up every single kind of function. But obviously, if you need to look up something, as I frequently need to look up just kind of like the reference in terms of like, oh, what's that exact argument or attribute or whatever that I need to do. That's fine. You're not restricted in that regard, but you got to get everything done within the time span, and that's probably the biggest challenge for me. Writing the exam is writing an exam of appropriate length that presents the right amount of challenge, but also is not like impossible for the students to complete in the time span. And yeah, it's always a little bit of like, how much time do I give myself versus how much time. So okay, so that's what we have for the final exam. I think that's that. And okay, so our last lecture today, final lecture for the quarter, I'll cover a little bit more stuff from Scikit-learn. And I'll say this again, I do have a favor to ask of you, and that is to fill out your course evaluation. And I hope you found the course useful. I hope you feel like you learned how to use tools in Python and whatnot to kind of do some data science stuff and data analysis and learn how to do some basic programming in Python. Obviously, there's only so much we can cover within one quarter, but I did try to touch upon a lot of kind of broad topics as well. But yeah, if you have feedback, anything to let me know, like in terms of like other things that you'd like to see in the course, let me know in the feedback. But otherwise, I hope you enjoyed the course, and if you're willing to give me the highest marks that you are willing to give, that is always appreciated. So, but you do have to fill that out before. I think the evaluation window closes on Saturday, tomorrow morning. So if you haven't done it already, please, I don't know, probably those of you who showed up today probably already have done it. But I guess maybe I'll send a message out to the class. Okay, all right. Let's take a look a little bit more at sklearn. And so again, sklearn is probably the biggest and most popular, and I would even venture to say one of the most important packages as far as machine learning on Python goes. And so what I will do is I'm going to load up, we're going to start off by loading NumPy, Pandas, and Matplotlib. And we're going to be using a few different things, but first I'm going to just go ahead and use a data set that is part of sklearn. So a lot of times we read in data using CSV files, but sometimes packages already have data sets, and they're, a lot of these are kind of like toy data sets or cleaned up or things like that. And so we're going to look at the Iris data set. Iris data set's kind of a very popular data set for machine learning and classification. It's got kind of this, a bit of a rich history in that like it was used way back, by like Ronald Fisher, who developed the F-test for, the F distribution and things like that. So, way back when, we were like learning how to do ANOVA for the very first time in the field of statistics and linear discriminant analysis and all of these kind of classical methods. But the data comes in something called a bunch. A bunch is like a dictionary, but the object, you have keys and values, and the values in a bunch could be something like a matrix or something like that. So like a dictionary, you can say, okay, what are the keys? And you basically get like dictionary keys, and it says, okay, here's the data and the target and the frame and things like that. Basically, the data is the X matrix, your matrix of predictors. And for the Iris data set, I'm not sure if you guys are familiar with the Iris data, okay? So here is so within okay, so here's the iris, and there are, I guess, we look at a flower and we just call everything petals, but apparently flower people, what do we call scientists who study flowers? Botanists, I guess. Okay, botanists, yeah. All right, so with botanists, they consider these things separate from these things, okay? So these are petals up here, and these things that I think the ordinary person would also call a petal, these are called the sepals, okay? So we have petals and sepals, and whoever developed this data set, like 100 years ago, they measured the length and width of the petals and the length and width of the sepals. And so we have 4 measurements: sepal length, sepal width, petal length, petal width. And there are different species of iris flower species. Okay. So we have the Setosa iris flower. Okay, so I guess this is a Setosa iris. I don't know. We have the versicolor, which looks like this, and virginica, which, okay, this looks the same. I'm not a. I mean, these all look totally different. So, okay, I don't know how good Bing's image search is as far as this. But apparently, as far as like how many iris flower species are there, there's like hundreds of iris flower species. List of iris species. Oh my goodness. Okay. There's a lot, right? So anyway, but this, oh my gosh, it still keeps going. Subgenus iris, subgenus limneris. Okay, well, it's a lot of, it's just a telephone, right? Oh yeah, so we can hear him say hello. Okay, but anyway, this iris data set, we're looking at 3 species: Setosa, versicolor, virginica, or in some other order. And we have those 4 variables: the sepal length, the sepal width, petal length, petal width, and things like that. So if I take a look at the data, it just has the 4 columns of the, sepal length, sepal width, petal length, and petal width is what these 4 columns are. Okay, we can ask, what are the feature length? Okay, and it says, okay, we have sepal length, sepal width, petal length, petal width. Okay, how big these things are. Okay, and meanwhile, the target is which species or subspecies, or which species of iris are we looking at? Okay, and we have 3 species that are included in the data set: Setosa, versicolor, and virginica. And so everything that's a 0, the first 50 observations, I think, we have 150 observations. First 50 are Setosa, flowers, and then you got 50 versicolor and 50 virginica things. Okay, there's also a description of the data set, and the creator is Ronald A. Fisher from whatever, a long time ago, 1936. Okay, and we are. So, this is interesting. So anyway, Ronald Fisher, we are grateful for his development and contribution to all of kind of statistics, but also, like, looking back historically, there was a lot of his work in statistics was he was a eugenicist, so that's a little bit problematic, but he was kind of a believer that, like, if we looked at these genetic components, we can identify like what the ideal human is like, which is certainly a little today we go, oh yeah, not so great. But yeah, you can see when it was his work published in 1936, multiple use of multiple measurements in taxonomic problems. They go, oh, okay, no problem. Where was it published? In the Journal of Annual Eugenics, and you're like, oh, okay, well, but yes, this, at least as far as classifying species of iris based on this, that does not present a ethical problem to us, but yeah. Okay, so we're going to use what we learned on Wednesday, train test split. So we'll take our entire data available, which is 150 observations, 3 species, 50 observations from each species, and we're going to split it into training data and testing data. So we're going to take the data part, which is the X components, the target part, which is what species they are, and we're going to split it, and we're going to do a 80-20 split. So for out of 50 observations, we're going to say 40 of them will go into our training data and 10 will go into our test data, because we're stratifying on the target. So we're going to get 10 test cases for each of our things. So when we ask for a shape, now we have 120 observations in our training data, and we can say, okay, what about if we take a look at our test vector, how many do we have of each species? And we have 10 of each of our species. Okay, so we've got, we can start off with using k nearest neighbors. So far we haven't done any kind of analysis. So far all we've done is the train test split, load up the data. Let's just create some plots just to kind of take a look. So I'm going to make a data frame out of the training data, and then I'm going to tack on. So I make a data frame out of the training data matrix, and I'm going to add a column called species, and we're just basically adding the column for the species in there. Okay, so if we do that, we get our observations back here. 5, 1, 3, 5, 1, 4, 0.2, and then some of these things. Okay, and we see. Oh, actually, this is an entirely different thing. Just because when we did the train test split, it randomized, right? It randomly selected 40 observations and it mixed it up. Okay, we can use Seaborn, and we can just do a pair plot. And so Seaborn pair plot will create kind of we have 4 numeric variables, and it will do variable 0 versus variable 1. So sepal length, sepal width, variable 0 versus variable 2. I probably should have named these things. Do I? Okay, so yeah, okay. Yeah. Well, anyway, when we do hue equals species, it colors each of these things, and so we can say, yeah, you know what? If you just look at variable 0 versus variable, say 2, you can kind of create these places to separate out the 3 different species of iris. Okay, so some of these things a little bit more clear, and some of these are variable 2 and variable 3 together. Very kind of clear distinctions. There's species 1 and 2. There's a little bit of overlap, but I would say this one's probably the one that we could use most clearly. But others of these kind of in conjunction with each of these variables, we can kind of start creating some way to classify these things. Okay, so again, Seaborn. You could have done any of these things in Matplotlib yourself, but again, Seaborn is just very kind of convenient. It allows you to kind of create these handy visualizations for exploratory analysis very quickly. Okay. Oh, by the way, no view quiz today. No view quiz. So just look at this for fun. So there's different tools. One of the tools we can do is called the k nearest neighbors classifier. So the k nearest neighbors, basically, you'll have a test point, and you plot the test point, And what you do is you say, okay, if the test point is like right here, we're going to say, who are the 5 nearest neighbors to this test point? And the nearest neighbors are found by measuring the Euclidean distance of that test point to every other point in the data set, okay? And you say, okay, who are the 5 observations that have the smallest Euclidean distance to this thing, right? So Euclidean distance is, x1 for observation A minus x1 for observation B quantity squared plus x2 for observation A minus x2 for observation B quantity squared. So on, Pythagorean theorem basically, but it allows it to work in higher dimensions. And we go through and we measure the closest ones, and then we say, okay, out of the 5 neighbors that are the closest to this observation, 4 of them were Setosa, and 1 was Virginica. And based on that, we're going to guess that this observation is Setosa because, 4 of the neighbors were Setosa, right? And so basically, every out of the 5 nearest neighbors, everyone gets a vote. And whichever group ended up with the most votes is the one that you're going to predict. So on some occasion, you'll end up in tie situations. Like it's possible to get like 2 votes for Setosa, 2 votes for Virginica, and 1 vote for Versicolor or something like that. That's possible. And in that case, you would probably just leave it as either unclassified, or you can flip a coin, or you can say, okay, well, between Versicolor and Virginica, the one nearest neighbor was Versicolor, or you could, go down and say, okay, between Versicolor and Virginica, the 3 nearest neighbors, 2 are Virginica, and 1 is whatever I said, and you can go that way to resolve ties. So ties is an issue with the k-nearest neighbors algorithm, and for something like this, k-nearest neighbors algorithm works pretty good. If you have a huge data set, though, like millions of observations, we would say don't use k-nearest neighbors, because what k-nearest neighbors does is you have to measure the distance from your test case to every other test case, every other point in your training data. And so if you have 1 million observations, you have to measure 1 million distances just to get like your top 5, right? And when you have it like plotted in 2D, you may be like, why do I have to measure the distance to everything? Obviously, these are the 5 closest observations. In 2D, our eyes very easy to recognize these things, so it feels silly. But if you have like 16-dimensional data, there isn't an easy way for you to know which 5 observations are the closest. So you end up having to measure the distance to like all million data points, right? And even just like the idea of like plotting 1 million data points, that takes a lot of time, right? So yeah, it's very computationally expensive, k-nearest neighbors, if you have a large data set. So in that regard, I would say k-nearest neighbors has fallen out of favor in production environments, just because in like production environments, you have oftentimes huge data sets, and k-nearest neighbors is very computationally expensive for huge data sets. Works great if you have like less than 10,000 observations, I'd say. And I don't know. I mean, probably as computer speeds get even faster and faster and faster, and like maybe the huge data sets isn't even a problem, but right now I'd say it is, okay? It's just computationally expensive. So anyway, how do we do this? We're gonna say, okay, from sklearn, within the neighbors subclass of kind of functions and modules and algorithms, we can load in the k-neighbors classifier, and then we're gonna create a k-neighbors classifier by saying, okay, we're going to look at the 5 nearest neighbors. That's going to be k and n. And so now we have a k-neighbors classifier object, and we do, let's fit the model. Fit the model as we have the x matrix and our y vector. We do that, and so now the thing is done fitting, and we can say, okay, now run predictions on the test values. Okay, and this is it. And this is like, we have our test values, there are 30 observations, and we said, okay, make predictions on these 30 observations, and it says, okay, I've run these 30 observations and I'm predicting class 2, class 0, class 1. And we can compare it to the actual values. And, you know, we go through and we're like, okay, this is a match, and this is a match, and this is a match. Can you recognize like where we have mismatches? I think we have a mismatch right here, the 1 and the 2. It's a little bit hard to kind of see. So one of the tools that we have, and this is under the metrics section. So metrics is a way how we measure our model's performance. So within sklearn metrics, there's a tool called the confusion matrix. The confusion matrix basically says if the true answer is a 0, our prediction is also a 0. Okay, so the true answer is in the rows and our prediction is in the columns. So what you want to see is values going down a diagonal, okay, for a confusion matrix, because those are like when the true answer is 0, when we guessed 0, that's correct. And we didn't, when the true answer was 0, we didn't get any wrong. When the true answer is a 1, we guessed 1 10 times, and we guessed 0 or 2 0 times, so that's a good sign. When the true answer was a 2, okay, we guessed 2 9 times, but we guessed class of category 1 time, right? And we can see that was this mistake here. The true answer was a 2, and we guessed a 1. So that reveals that we made one mistake. And out of the 30 observations, we made one mistake, okay? We can say, all right, what if I did the 1 nearest neighbor, okay? So I'm doing the k-neighbors classifier with number of neighbors equal to 1. We fit on the training data. We run it through the test data, okay? And we ask for the confusion matrix. We end up getting the same kind of performance, okay? What if we use the 25 nearest neighbors? Here with 25 nearest neighbors, we actually get slightly worse performance. It's a little bit hard to do with and our data, just because like when you look at some of these plots, there's like very clear boundaries between the 3 classes, so it's relatively easy to get pretty good performance, and like you have to like really try to almost like search out for models that perform poorly. But in a lot of other kind of cases, maybe your data is a little bit more mixed. Like if you can imagine having a data set where the data only looks like this and you don't have like kind of clear boundaries over here. So if it looked only like this, your choice of how many neighbors to use is going to play probably a more important role as far as like how many mistakes and correct classifications you get. And it's depending on the data, sometimes it's very unreasonable to try to expect very good, model performance or things like that, and in some cases it's just like, the values, okay, just won't be there in the data, okay? So, like again, with like Ronald Fisher doing like eugenics stuff, he believed that like you could look at, genetic traits of people and like classify stuff, and for a lot of these things, like it's just not in the data, right? In the data, you're not going to be able to kind of like separate out these different kind of classes of things like that. And so sometimes, k-nearest neighbors certainly is not going to give you an improved performance or things like that. Okay. What do we want to do? So here I just kind of tried out 5 nearest neighbors, 1 nearest neighbor, 25 nearest neighbors, and we're looking at kind of performance. Rather than saying like, okay, what if we could repeat this and I could copy and paste like 1 nearest neighbor, 2 nearest neighbors, 3 nearest neighbors, 4 nearest neighbors, and see how we perform, we can use something called grid search CV. This is grid search cross-validation. And what we do is we kind of create this basically a series of different kind of conditions to use. And we can say, okay, I want to create a k-nearest neighbors model with 1 nearest neighbor, 2 nearest neighbors, 3 nearest neighbors. And so I'm going to create what we call this parameter grid. And for number of neighbors, okay, so in the dictionary, I have to use, when you define your k-nearest neighbors, one of the arguments is n underscore neighbors. And I'm going to say for n underscore neighbors, try out this array, okay, array of values going from 1 through 50. And we're going to basically run a whole bunch of these models here, okay? And then k-nearest neighbors also has a weights option, and you can have uniform or distance. And so remember the way I said the k-nearest neighbors works is we said, okay, you look at your 5 nearest neighbors, and each of those neighbors gets a vote, and we say, okay, we have 4 that are Setosa and 1 versicolor, and therefore we're going to do that. And uniform means everybody's vote counts the same. But you can also change that, and you can say, okay, weights are based on distance, okay? And we're going to say, okay, the people are the observations that are closest to your test case, like their votes count for more, okay? And so, you can imagine some kind of, for a company with a shareholder meeting, basically if you have more shares, your votes count for more, and other people who will have fewer shares, their votes count for less. And we have something kind of similar. I think it's like an inverse distance thing. So closer distance, their votes count for more, and farther distance count for less. And so we can say, all right, is that going to improve our performance and things like that? Okay. And we can say, all right, set up our k-nearest neighbors classifier. Notice we don't put any parameters inside here this time when we specify k-nearest neighbors versus like back here we said number of neighbors is equal to 25. Here I leave that blank, and then I run the function grid search CV. We're going to run the KNN classifier that we just defined here, and we're going to run through all of the different parameters in the parameter grid. And we say, how do we evaluate the performance? We're going to do cross-validation. So again, cross-validation, you subset it and you say, okay, we tried on this, 80% and tested against this 20%, and we kind of mix those up. We shuffle them up each time. And so we do that, okay? And we're going to run it on our training data, okay? So we're going to do KNN cross-validation, and we're going to run fit on our training data, X-train and Y-train. So we run through it. It takes a little bit of time because we've got basically 100 different sets of parameters to try out, right? 1 through 50, and also uniform and distance, or maybe only 49, maybe 98 sets. Okay, it's something like that, okay? And we can say, okay, what were the best set of parameters to use? And it says 13 neighbors with uniform weight, and our best score, okay, I mean, we're still only getting, we're not getting 100% performance. So we could say, okay, how well did it perform on the training data? And we look at our confusion matrix, and basically we made 2 mistakes when we had 1, and for category 1, we guessed it was category 2 times out of that. Okay, so we got this correct 118 times out of 120, and that's where this best score is coming from. And we can see how well does it perform on our test data. We end up getting like the same performance that we've seen back here, but this was apparently kind of the best performing thing. And anyway, that's what we see. Okay, so we can kind of get a breakdown of the cross-validation scores, and in each of these things, when we did it, there's only there's 120, and we divide 5, so out of 16, we're getting our performance on those data points there. Okay, we could try out another classification method. So another classification method is the naive Bayes classifier. I don't feel like explaining all of how the naive Bayes classifier works, but it's a commonly used algorithm as far as trying to make a classification, and the basic, It's naive because it's assuming all of your variables are independent, and it's the Gaussian naive Bayes because we're assuming our numeric values follow a normal distribution. And for the iris data set, I think that's reasonable. Like, you look at the distributions of each of these kind of species, and they look fairly normal, so it's probably fine to use the Gaussian or normal naive Bayes classifier here. And so anyway, we're going to create a new naive Bayes classifier model. We fit it on our training data. We say make predictions for our test case. We say let's look at the confusion matrix, and again we get pretty good performance. I think this is like this one observation, and it's even though it's like class versicolor, according to its measurements, it really looks like one of the other flowers, and so we keep kind of misclassifying this this one observation, but that's what we have. Okay. In real life, it's pretty rare to get such high classification performance, except in kind of like the most, toy data sets. And so again, the iris data set, we have this, it's fairly clean and something like that, but in a lot of other cases, you're going to get a lot of kind of misclassifications. All right, and then as far as cross-validation scores, we can say, okay, how did it perform with cross-validation? We get pretty similar performance, and overall, when you take the average of all of these things, you get 95%, meaning you misclassified around 5% of these things. But this is just kind of like very basic examples of fitting some kind of machine learning model. Right here, we just looked at two of them: the k-nearest neighbor, Gaussian naive Bayes classifier. But you can see all of them kind of follow the same form, and it's just a matter of kind of just changing up the thing. But you basically say, all right, and we're going to import this kind of module or this function here, and then you define an object with that, and you can provide any kind of additional arguments to kind of change our parameters to change how the classifier is going to work, or how your machine learning algorithm is going to work. And then you fit it using XTrain and YTrain. And again, you need to have a matrix of your training data and a vector or an array, a one-dimensional array of your cases, the answers for these supervised learning things. And then you make predictions on your test data. So all of this, we've used kind of the model selection tools like train, test, split, and cross-validation to kind of measure our performance there. Okay, again, if you've never learned too much machine learning, I'd say, be careful. You don't want to just start applying machine learning algorithms blindly. But I did want to kind of touch upon this just because I know some of you have already been exposed to machine learning ideas, and I'd say Python is quite popular for applying machine learning algorithms, just because it does generally give you pretty good performance. Okay, that is it for today's lecture, and I guess that's it for all of our for the entire quarter. So good luck as you study for the final exam in this class. Any other finals that you have in any of your other classes, and it's been a pleasure being your teacher. Thanks for coming today, and have a great winter break. And I think some of you I'll definitely see in the future, and others of you, like, I maybe not have a class with you again, but probably maybe I'll see you at graduation or something like that. So, all right, okay. Thanks. That's it. Have a great rest of your day.